Okay, today we are talking about solving logarithmic and exponential equations. I suppose it's the other way around in the section, but section 3.5, we're going to start by solving an exponential equation by hand. You could always solve an equation like this by graphing, but for the purposes of this section, we're going to solve them by hand. So the first thing I want to do is I want to isolate my exponential. So that means I'll divide both sides by 20. Giving me 1/2 to the x over 3 equals 5 over 20 is 1/4. Now I'm going to try to get the bases, the 1/2 and the 1/4, to be the same. So 1/4 is equal to 1/2 squared. That's 1/2 times 1/2 is 1/4. So 1/2 squared, they should all, some of them should work out. If not, it's a logarithm that you will need to use to solve these. And we'll go through an example of that in a second. Now that my bases are the same, since they're both 1/2, I can just set it equal to the exponents, because 1/2 to 1 power has to equal 1/2 to the same power. So x over 3 has to be equal to 2. I will multiply both sides by 3 and get x equals 6. That is my first example. That's example 1. Now we're going to do example 2. Example 2 is going to involve a logarithm and a couple other things. So this is e to the power of x minus e to the negative x over 2 equals 5. First thing I want to do here is move the 2. So multiply both sides by 2. Now comes a little trick. And the trick is I'm going to multiply everything by e to the x. The reason I want to do that is I don't want this e to the negative x. I don't like it. It's not helpful. So this is going to get me e to the positive x. So e to the x times e to the x is e to the x squared. You might see it written like this, e to the 2x. I'm writing it like this for a reason. E to the x times e to the negative x. When I multiply these, I add the exponents and I get e to the 0, which is just 1. And then 10e to the x. I'll subtract the 10e to the x to the other side. And I get e to the x squared minus 10 e to the x minus 1 equals 0. This kind of has a quadratic type look. So I'm going to use this little thing called the substitution variable. The standard substitution variable in math is u. So u equals e to the x. That allows me to change the e to the x's to u's. I don't know why I made that an equals. And now I have a quadratic. I can use the quadratic formula to solve for u. So u equals 10 minus the square root of 10 squared is 100 minus 4 times a times c over 2 times 1. 10 minus square root of 104 over 2. I'll reduce my 104 here. That's 4 and 26. 2 and 2. 2 and 13. I got a pair of 2's. So giving me, I'm going to come over here on the side, u equals 10 minus 2 square root of 26, there's a 2 and a 13 left, over 2. I can reduce my fraction by taking it from all of them. Really important that when I reduce, I take from each term. No, that's a 1. 1. So I end up with u equals 5 plus or minus the square root of 26. Okay. Problem is I don't need u, I need x. So that means I've got e to the x equals 5 plus square root of 26. I'm going to separate them now. And e to the x equals 5 minus the square root of 26. If I can, there's a couple ways to do this. I'm going to go with the one that I prefer. You could change to exponent or logarithmic form, which is essentially what I'm doing. I'm taking the natural log of both sides. I'll do it to that one. I'm going to do it to the other one too. I'm just going to write it in there. Natural log of e to the x is simply x. And that gives me, if I use a calculator, I get approximately 2.31. You could also leave the answer as natural log of 5 plus square root of 26. When I do this one, oops, take my natural log on that one. Natural log of 5 minus the square root of 26, taking the natural log of a negative number. This is not defined or not real. That one doesn't have a real answer. So this is my only solution. One of the keys, though, you can do this substitution, use the quadratic formula, but you must substitute it back and solve for x, not just solve for u. Now we're going to solve a logarithmic equation. This is example 3. It's a pretty basic one. So I'm going to start by converting to exponential form. Remember, this is base 10 if it's not written. So when I convert to exponential form, I do base, the power of the opposite side. And you might just recognize that that's 10, but if you don't, actually, it's more than 10. So I square 10. I'm going to square root both sides. And when I take a square root, I must introduce a plus or minus. Square root of 100 is 10. Yes, this does work. You do have to have both because negative 10 squared is still 100, and that's a positive before I take the logarithm. A harder exponential equation, or a logarithmic equation, this one I'm going to have to use the laws of logs for. So before I proceed further, I could set it equal to 0, but what I think I'm going to do is just get an ln on both sides. So working on my left side, I know that the plus means I can multiply them. Working on the right side, I know I can bring the 2 up to the exponent using my laws of logarithms from the other day. Since I've got ln and an ln, I know the insides must be equal. Another little trick you can look at is I can do e to the power of, and that'll cancel my ln's. So I've got 3x minus 2, x minus 1 equals x squared. This is a quadratic equation. I'm going to FOIL this out. 3x squared minus 3x minus 2x plus 2 equals x squared. I'll subtract x squared from both sides and combine like terms. 2x squared minus 5x plus 2 equals 0. I can factor this, I believe. 2x x minus 2 minus 1 equals 0. My solutions are here. X equals 1/2 for the first one. 2 times 1/2 minus 1 is 0. Again, if you're not sure on how to solve that, write it out, solve the equation. And the other one is 2. Now, here's the problem. I must go back and check my answers, which means I got to plug them in. ln of 3 times 1/2 minus 2. That's 3/2 minus 2 is negative 1/2. That's the ln of a negative number. This is extraneous. Ln of 3 times 2 minus 2 plus ln of 2 minus 1 equals 2 ln 2. So that's ln 4 plus ln 1 equals 2 ln 2. And that's going to work. That's ln 4. ln 1 is 0. Any logarithm 1. And this is ln of 2 squared. So I've got natural log of 4 equals natural log of 2 squared. 4 does equal 2 squared. I'm going to do a couple of things here. And we're going to talk about the Richter scale. And the Richter scale is a measurement of how severe earthquakes are. Here is the equation for the Richter scale. We'll talk about the pH scale in a second too. These are both logarithmic scales. We also talked about the decibel scale the other day. Are 3 very common logarithmic scales. I've often seen this one written as log I over I0, where I is intensity of ground movement, I0 is the amount of movement, because molecules are always vibrating at any temperature but absolute 0. So the ground is moving. So I0 is just the standard ground movement when we consider it not moving. Yes, it's moving. We can't tell. It's so small. So what we're going to do is we're going to compare severity of different earthquakes. Okay, we've got an earthquake in India, in Gujarat, which had a Richter scale magnitude of 7.9. That occurred in 2001. In 1999, we had one in Athens, Greece, that was 5.9. We want to compare how many times more severe the 7.9 was than the 5.9. So we're going to look at our equations. And I'll use the ones the book is using. This is example 5. And I've got 5.9, A1. B is Standard, B is a standard, it's the same in both of them. B accounts for the weakening of the seismic wave based on the distance from the center. So this measurement is at the epicenter, or basically the center of the earthquake, and it spreads out in a circular pattern. So B has to do with distance from that. Okay, we're gonna set what I'm standard gonna do here is essentially R1 minus R2, which means I'm just gonna subtract these two equations or add a negative. It's easier to see it as add a negative. Gives me 7.9 minus 5.9 equals log A1 over T plus, no, not plus, minus log A2 over T plus B minus B. For here, we're assuming we're the same distance away. Basically, I'm looking at it as the center. At its center, what's the difference? So if 7.9 minus 5.9 is 10, using the laws of logs, I can get A1 over T over A2 over T. And I'm going to simplify that. A1 over T, when I divide fractions, I multiply by their reciprocals. And this is simply A1 over A2. My T's cancel out. When I multiply, I have one on top, one on bottom, so they just cancel. What I'm ultimately trying to do is find out how many times more severe A1 was than A2, which means I'm looking for the ratio A1 to A2. So here I have my base 10 log, and to get my A1 over A2, I just convert to exponential form. Base to the second, 10 to the second equals A1 over A2. That's 100 times worse. The little blue thing here is a 10. I wrote it kind of small. It's 10. Just writing in my base to help when I convert to exponential form. Okay, that's example 5, the earthquakes. We're going to talk for a second about pH of, well, we're going to use pH. And here's my pH scale. You should have used this in chemistry, but negative log, that's base 10, of the concentration of hydrogen ions in a acid or base. So it's in a mixture with water. So we have two pHs. We have vinegar, and it depends on the strength of it, what the pH will be. This particular vinegar is 2.4 for pH, and baking soda. This baking soda water solution is going to have a pH of 8.4. So when we talk about the pH of baking soda, we're talking about it when it's dissolved in water. So we're just going to get both of our pHs. Oh, wait. Vinegar, 2.4 equals negative log H plus. We're going to get our H plus, our hydrogen ion concentration. So I convert to exponential form. Again, it's a base 10. Oh, no, first thing I need to do is move the negative. That's 10 to the negative 2.4 equals H plus as I've converted, which is equal to 3.98 times 10 to the negative third. The unit on H plus is moles per liter. So this is vinegar. Baking soda, if you see the pattern, I just negated the pH, 10 to the negative of the pH. It's going to give me H plus. You could work it out again with the logarithm, but this one is 3.98 times 10 to the negative ninth moles per liter. So it says how many times greater? How many times? Well, we're going to do one divided by the other. Or the easiest way to do it is actually to take these, 10 to the negative 2.4 over 10 to the negative 8.4. And that is 10 to the negative 2.4 times 10 to the positive 8.4. I add the exponents and I get 10 to the sixth, or a million times more. Vinegar has a million times more, million times, not a million times as many hydrogen ions in the dissolved water. We can talk about this in terms of orders of magnitude. I don't know if you guys have heard of orders of magnitude in science. An order of magnitude is how many 10 times. So this is 10 to the sixth is 6 orders of magnitude. Orders of magnitude just means take the exponent when I'm talking times 10. Since the reason we're talking about times 10 is that we use a base 10 number system. 10, we've got digits 0 through 9. Then we've got 10 through 100 is all 10, or 10 through 99 is all 2-digit numbers. Then 100 through 999 is 3-digit numbers. We're multiplying by 10 every time. Okay, it is time to talk about Newton's law of cooling. Now, Newton's law of cooling, this also applies to warming, but it talks about how the temperature of something changes when you put it in a colder environment. So everybody here has probably had a cup of hot coffee or tea or hot chocolate or something where you have left sit out and it's cooled. Or you've gotten something out of the oven. And we're going to talk about what all of these mean in just a second here. So here, little t stands for time. Time since it's been in the surrounding environment, or time that it's been cooling. So you get cookies out of the oven. That's as soon as you pull them out of the oven, they start cooling in the room around them. That's when time begins. T of t is temperature at the time. So maybe T of 30 would be temperature 30 minutes later. That's current temp. So capital T is mean temp. Tm is surrounding temperature. So that would be, if you put them in a room, that's the room temperature. Clearly the cookies are going to cool faster outside on a winter day. T0 is initial temp. So this is the temperature of the cookies, say, when they come out of the oven. K is a constant of proportionality, which has to do with, I don't know if you guys learned about specific heat in chemistry, but specific heat says how much energy needs to change for temperature, for the temperature to change 1 degree. You probably know that metals heat up and cool down way faster than, say, water. Water's pretty slow. So we're going to end up calculating K here. And it's not exactly the same as the specific heat, but it's the same idea. They're proportional. Specific heat is something you'll calculate in chemistry. So a hard-boiled egg at temperature 96 degrees Celsius is placed in 16-degree Celsius water to cool. 4 minutes later, the egg's temperature is 45 degrees Celsius. Use Newton's law of cooling to determine when the egg will be 20. So I know I've got T of 4 equals 45, and I'm going to use that to get my K. I know my initial temperature was 96, and my TM was 16. So it's all in Celsius. So pretty close to boiling. So initially, I'm going to plug in knowing everything but K for this 14-minute case. So I plugged in that specific case. I'm asked when it equals 20, and we'll get to that in a second, but let's solve this. I'll subtract 16 from both sides and get 29. 96 minus 16 is 80. I'll divide both sides by 80. Here, I subtracted 16 there. And I get 29/80ths equals e to the negative 4k. I'm going to take the natural log of both sides or convert to exponential form or logarithmic form. They end up being the same thing. You get ln 29/80 either way. Natural log of e to the negative 4k, natural log of e to a power just cancels, and I'm left with the negative 4k. And I get ln of 29/80 divided by negative 4. When you put that in your calculator, make sure you close the parentheses on the 29/80 before you divide by the negative 4. This is approximately 2.53. I can now use that to get when it's 20. I'm just going to use the 80 again. Negative 0.253 t. I'll subtract 16 from both sides and divide by 80. I'll subtract 16. So I'm going to do my same process of solving. Divide by 80. That's 4/80 is 1/20th. They didn't reduce it in the book, and I'm not sure why. E to the negative 0.253 t. So again, I'll ln both sides. I'm not writing it in this time. And then I'll divide by negative 0.253. Giving me a time of approximately 11.81 minutes. This has cooled rather quickly. Okay. Now we're going to talk about modeling. And if you look at example 8, they've got a temperature data on the side of page 327. And I've got that in my calculator here. So I am going to do an exponential regression. Now, the key thing they did here is they did t minus tm. Okay. The reason they did that, didn't just enter tm, is when I do an exponential regression, my default puts my horizontal asymptote at 0. Well, tm would make my horizontal asymptote. That would be Tm. So to move that down, I just subtract Tm from every value. So this is actually the temperature minus the surrounding temperature. And that shifts it down for me. So to calculate this, I'm going to clear those off for a second here. I'm going to do stat. And then I'm going to go to calc. And I'm going to do ln reg. ln reg. No, I don't want ln reg. I want exponential reg. ln reg would be a logarithmic regression. I want exponential regression. My data for this one is an L1 and L2. I'll store my regression equation in y bars y1. And my equation is (61.656) times 0.9277 to the x. I like to keep a lot of variables, especially on the exponent here. We'll take a look at our stat plot. Let's turn this one on. And this one off. And then I'm going to go substat. And that looks pretty good. So that was an expression with Newton's law of cooling. Now, the surrounding temperature on this one was 4.5. So if I really want the temperature equation, I should put the plus 4.5 back on here, because this was y minus 4.5. Oops, there's no parentheses at the end. Okay. The last one we're going to talk about is logarithmic re-expression. And we did a little bit of this the other day, but we're going to do a little more. So I've got my data in L3 and L4. So I'm going to log both axes and take a look at what's happening and making a video. Hello. So we are going to log both axes. Okay. So I'm going to do ln of my data's in L3, and I'm going to store that in L5. So I do ln L3, store L5, hit enter, and I will do the same thing with L4. ln L4, and I'll store it in L6. And I'm going to do, so I want to know what's going to turn this into a straight line. Okay, couple of things to note. If I have just x and y and it's linear, that's a linear equation. If I have ln x, so I've ln'd the x-axis but not the y-axis, that is logarithmic. And I can look at the graph and usually tell, sort of. If I do x versus ln y, this is exponential. And if I do ln x versus ln y, this is the interesting one. This is power law. So it's a power function, like y a b to the x. So we're going to take a look here and see. What I'm going to do here is just look at different stat plots. I'm going to make this one. So we'll do them in order. Actually, I'm going to do L3, L4 first. And take a look and see what I think. guess I can turn off my y equals. This is definitely not logarithmic. It's curving up. So this is either exponential or power law. It could be either. I'm going to go to y equals here and turn this off. And then I'm going to go to stat plot. So I'm going to try exponential. So we're going to do x versus ln, which means I had ln of y in L6. So let's take a look at what that does. That now looks kind of logarithmic. So it's kind of curving a little bit this way is what it looks like. So let's try and see if it's power law. I'll undo that drawing. Power law, I'm going to try both axes. That looks kind of straight. So we're going to do that. We're going to try that one stat. And I'm going to calc. I'm going to do a linear regression. I'm actually going to do a plus bx. It's easier in this case. And I'll show you that in a second. But this needs to be L5 and L6. We'll put this in Y1. Okay. And that looks like it fits the line rather well. Yeah, it fits rather well. And it just locked it for me, so I guess I have to do it again. Okay. I'm doing a video. It's okay. Okay. So my equation, and I'm going to go to a whiteboard for this, 0.5827, 1.647. I'm doing a video. So just give it a second. It's okay. Hey, quiet. I'm doing a video. So I've got y equals 0.582799 plus 1.6472 x. Now here's the thing, both of these axes are natural logs. Did I get that number right? 582799. So what I'm going to do is I'm going to bring this up to the exponent, and then I'm going to bring them together. Eight two seven nine nine. That's the correct number. I'm making a video. So actually, what I want to do, I don't want to do that. Never mind. I'm going to do e to the power of both sides. So that's going to be e to the lny equals e to the 0.582799 plus ln x to the 1.6472. E to the lny, those are inverse functions, just becomes y. Now, there's a really cool property here on using the exponent rules. When I'm adding exponents, they're like bases. So I can say e to this power and e to the ln x to the 1.672. That cancels, or the e to the ln part cancels, not the x. Just this part. Giving me, and I'm just going to use my calculator to get e to the 0.582799, which is 1.7910. Again, I'm just calculating this, and that's that. And this is my power law equation. Ax to the power of 1.6472. That fits my data. And that is the end of 3.5.